Alright, so this is where we left off. This was the next question in the chapter. Let me get this off the screen. So, this was the next question in the chapter. Right here. And so, this is where we were at yesterday. So, can someone tell me what we did yesterday? What was the overarching theme? So, let me put a 1 here for somebody who's going to tell us that. Overarching theme. What did we do yesterday that is like the beginning of the class, or the beginning of this chapter? Can someone tell me? Derivatives. That is correct. So, let me put that up here. So, we did I don't know if that's spelled right, but I'm going to trust you on that one. Derivatives. So, derivatives. That is like the main thing we talked about. And derivatives of what? We derived the scalar equations of the vector loop, like this right here. We derived those equations to get the velocity. So, and acceleration equations, right? Do you guys agree with that? That is what we did yesterday. And there was one more thing that came out of that, is that we got things known as H's and F's. Well, we didn't get any F's yesterday, but maybe if you guys try hard enough, you can get one. So, but today we will get one. In this question, you will get an F. And I'm saying that as this right here, not that you will get an F on the exam, but who knows. So, what are these things called? Did anybody know what they were called? These H's and F's? I did say it yesterday many times. What were they called? I'm going to start you off with the first one. It was kinematic. Kinematic. Here, ready? I'm gonna do one letter at a time while you guys finish the puzzle. I have a typer. Coefficient, yes. So it is a kinematic coefficient. 10 points to Gryffindor. So, kinematic coefficients. And remember that kinematic coefficients, so for example, H's is equal to d theta over d theta 2. Right? That was like, so that is the derivative of whatever angle we're looking at. So like say it's link 3, it's the derivative of link 3's angle with respect to the initial angle, which is this theta 2 input, right? And likewise, F was d r over d theta 2. But remember, these things do change depending on what the input is. So for example, if your input is a r instead of an angle, this would change to R2 and R2. But everything else is the same though. So this would just go R2 or R2 here. So your input always goes on the bottom because we're taking it with respect to the input, whatever we're putting in. Cool. So let me go ahead and get rid of this part right here. So this is sort of the overarching theme of what we did. John Lynn, you got something for us real quick? All right, and so what we're going to do today is we're going to do this next question. So this next question is a very simple one, just like the one we did before, except that it involves a slider this time, right? So we now have a different type of equation than we did before in the 4-bar mechanism, such as this. So this one has a slider in it. Now, as you guys can see, the vector loop has already been created, right? We're going here, a negative vector back towards us, a negative vector of 4, and a positive vector of 1. So that means we have R2 minus R3 minus R4 plus R1 is equal to 0, right? If you just follow the vector loops, follow the arrows, you will get that equation. I think everyone's pretty much figured that out, hopefully, right? So we're going to write the steps of these questions over here in this corner. So step 1 is to get the vector equation, so just the vector loop equation. So the vector loop equation, right? And that's what we have here. This is step 1. Step 2 is to get the scalar equations. So the scalar equations are obviously based off of the vector equations, which are the x and y components of the original vector loop. So let me write that. So we have scalar equations. And so the scalar equations for this are R2 cosine theta 2 minus R3 cosine theta 3. Oh man, it's better not. It's not that bad. I thought it was worse than it was. And then plus R1. Now, because once again they did a nice trick with their coordinate system, R1's angle is 0, so therefore we leave R1, wait a minute, what did they do here? Oh, I was looking at R4, now it makes sense. Okay, wow, I can't believe I did that. I thought they numbered it differently. Okay, let's get back to that. So, we did R3 cosine theta 3, and then R4 is this one right here. R4 is the slider vector. So if you do the cosine of this angle, you will get 1. So therefore R4 just goes to R4, right? And then R1 is this vector going up to here, this little tiny vector going up to here. And if you take the cosine of that, you'll get 0. So that's why we'll get to here. Yeah, I gotta watch that one. They changed the sign, they changed it on me. So that is our first one. That is the x equation. The y equation, similar. You just take the signs this time. And then R4, which goes away this time. R4 goes away because the sine of an angle of 0 is 0, so we get rid of that. And then R1 stays because you take the sine of an angle of 90 degrees, you get 1. Right? So that is step 2. Step 2 is scalar equations, right? I think everybody has gotten this so far, right? So we go vector loop. If you have to create the vector loop, the first step is obviously to create that. But for this question right here, we were given the vector loop, so we start off with the vector loop equation. But if it happened to be blank, then you would have had to create it yourself. So, vector loop equation, scalar equation, third one, which I'm going to do over here, is the derivative. And so this is the derivative of the first set of equations. So we are doing the first derivative of these two equations. So I'm going to start with the x1. The x1, you would do R2, well, negative R2, sine theta 2, right? Just like yesterday, we take the opposite of this one. So cosine's derivative is negative sine, so you put a negative out front and you have a sine here. Now, minus R3 cosine theta 3. So for this question, we know R3 because R3 is just this vector length at all times. It does not change at any point into this. So therefore, R3 is not a variable, but cosine or theta 3 is a variable. So that means, as we said, we do the derivative, we do r3 on the outside, and then we take the derivative of this. And the derivative of this, although I should change that sign, the derivative of this is plus r3 h3 sine theta 3. And the reason we got an h3 was because we took a derivative of of the angle in the middle. So for things like this, you do the derivative of whatever's on the outside, so you do the derivative of cosine, and then you multiply it by what the derivative of the inside was. And the derivative of the inside would have been this, if you write it out. It would have been d theta 3 d theta 2. And we've already made that, we've already made it known that that right there is substituted for h3, right? So everybody's all good on that. Can I get a 100 in the chat? If if that's understandable, if we're all good, or a GIF that says yeah, I got it. All right, cool. So we're all there right now. So now this is where this question changes in comparison to our last ones, right? So now let's move on to R4. So R4 is right here, right? Is R4 known or unknown in this question? Anybody want to take a crack at that one? It is unknown, correct, gentlemen. And the reason is because as this moves this way or back this way, R4 is changing, right? Pretty clearly it's changing. So we have to take a derivative of R4. What is the derivative of R4 with respect to theta 2? It is this right here. What is that? What is the derivative of R4 with respect to theta 2? Ooh, is it though? 0. Junlin has just sent me F. The answer is F. You got something, Jackson? Let me slide down. Yeah. Oh, shit, I gotta get back up there. Would that be implicit differential? Are you talking about like implicit differentiation? Is that what you're talking about? Okay, that. No, because remember what this is actually, this placeholding thing right here. Essentially, what it is this. It's just so it's the derivative of R4 with respect to theta 2. So essentially, it's like saying this. It's like saying dx dy essentially, right? Or dx4 in this case. With respect to y, y is our input, or our out is our input, and we right here, this is an output. So essentially, it's just taking a derivative of one with respect to the other. And so right here, this is just a placeholder. So remember, this R4, when you get an F4 here, so which is what we're gonna have, which is an F4, it's just a placeholder for this right here. So basically, let's put it this way: when you take a derivative of a vector length that is changing, replace it with an F4. And F4 is the kinematic coefficient that represents this right here. Yeah, it's the beach doing it to you. You should get some shade, drink some water. So, we have R2 sine theta 2 plus R3 H3 sine theta 3 minus F4 is equal to 0. Right? That is our first equation. We have taken the first derivative of this one. Now we have to do the y one. So let's do the y one. So we have the same thing, R2 cosine theta 2. Remember, we're on opposite functions, so this is just going to go to cosine. And then right here, this will be minus R3 H3 cosine theta 3. Correct? And then R1. Is R1 changing in any way? So just to let you guys know, R1 is right here. And you are correct, Rosendo. R1 is not changing. It is always going to be that length right there. So therefore, what is the derivative of something that is always known? Or constant, I guess you would say. Zero, correct. So we now have removed that one from the equation. Therefore, we have this as our next equation, right? Pretty straightforward. This is what we got. Because this one goes away with the first derivative. Now we have to do the second derivative of this equation, right? So does everybody have this written into their head? Because I'm going to delete this one and then, actually, I'm going to delete this one over here. If only I write smaller. So I'm going to get rid of this one. Alright, so that's 3. This is first deriv, second. There. So now we are on to step 4, which step 4 is the second derivative of the original scalar equations. So we're going to start off really fast by doing R2 sine theta 2. So that is this one right here. We're going to do this first one. So we're going to this one will be minus R2 cosine theta 2. And now we have to do plus R3 H3 sine theta 3. So remember, R3 is just a constant, so it sits outside of the derivative. And on the inside, you take the derivative of H3 first and leave sine theta 3 the same. So H3 goes to H3 prime multiplied by sine theta 3. And then we add the derivative of this sine theta 3 while leaving the other one blank. So we have H3 stays there, doesn't change, times another H3 because we did a derivative of this right here, sine theta 3, which brings out another H3, and then we go cosine theta 3. So in reality, that's H3 squared. So I will get rid of that. But I just wanted to show everybody where that was coming from. So H3 squared. All right. And then, what is the derivative of this last part right here? What is F4's derivative? It works the same way as the other kinematic coefficients that we took a derivative of. What is F4's derivative? Which is the last part. It's this right there. Anybody? Anybody take a shot at this one? So F4's derivative is just F4 prime. Just like it was with H3, right? And you know what I mean? You just take, if you take the derivative of H3, it goes to H3 prime. So F4 prime is where we're at now at the end of that. Let me mark this off. All right. Now we have one more to go, which is R2 cosine theta 2, R3 H3 cosine theta 3. So once again, pretty straightforward. We take the derivative of this minus R2 sine theta 2, sin theta 2. That is a 3. Right? And then we have this one minus So once again, you pull out an R3 because it is not changing. So we are going to leave it as a constant on the outside of the derivative. And then we do H3 prime cosine theta 3 plus, although that's going to change to a minus sign here in a second, but I'll do that now. So minus H3 squared sine theta 3. Right? So this is our second derivative of both of these equations. So first derivative was here, second derivative here, and our initial equations were the scalar equations we found before. Right? Is everybody on point with this right now? Because this is all you're going to have to do. So for your homework and your exams, I will give you the vector loop such as this, right? I will give you the vector loop and with the labels of R3 and R2 and all that, and you are going to return me this. That's all you're going to have to do, is return me that, which is the... Oh man, I really need to block gifs in this chat. Anyway, so is everybody good with this right now? I know Sean just typed in ye, so but everybody else is good with this. They understand where we've gotten everything. All right, cool. So I'm going to delete this off the page, and then what I'm going to do is we're going to move on to the next example. So these are going to get a little more tricky, though, and I'm going to find one that is a bit more tricky to where it involves other equations. Not just, like, for example, a rolling contact will be involved. Because remember, we're not just taking derivatives of the scalar equations. Other equations need to be derived as well, if we have them. So this question did not have them because we had two equations and two unknowns, right? Oh, what is the matter with you? Anyway. So, and their final answer looked a lot like ours, right? So, here it was. So, good job, guys. Now let me find the next one. That's not one we really want to do. I want to find something better than that. Let me find something better than that. That one really sucks. We're not going to do that one. So that's funny because on this one, R2 is the input, if I recall. Yep, okay. So we're going to do this one right here. So we're going to do, let me zoom it in here. We're going to do this one right here. All right, guys. So this right here. So this one, can anybody see how this one is different than ones we've had before? Like, why is this one different than what we've had before? Remember that link 2 is always the input, right? That right there. But how is link 2 in this question different than any other time we've had? It is horizontal. Yes, that is one way, definitely. What does that mean in respect to the input? Is theta 2 the input here? Junlin's got something for me. Maybe. The answer might surprise you. Mathematicians hate them. You say theta 1. It is, so R, so Junlin is correct. R is what's changing here. So you remember when I told you that it could be a theta 2 or a theta, or an R2. This could be our input. So for this mechanism moving, right? So if you look at how this mechanism is moving, as you push or pull it back this way, right? Right? This R essentially is our input. We are essentially pulling or pushing it this way. So we're going this way, back and forth, back and forth, back and forth, and it is moving this pinball, slapper thing down or further this way, right? Does that make sense? Essentially, the way somebody made a good point the last time. They said that this mechanism is dumb because if you pulled this way, or if you pushed it this way, like if you went this way with it, this flapper would just fall down. And so one of my students, in order to defend the question, said that this. So try and imagine that this is spring loaded. So essentially, if this is spring loaded, it's always going to maintain contact with that, right? Would you agree? If it wasn't spring loaded, I agree with you. If this was just a pinned joint, this would be falling down and this wouldn't work. So you have to imagine that this thing is always contacting right here. No matter what, it's always contacting. So keeping that in mind, what is step 1 of this question? What is step 1? So somebody tell me what the vector loop is here. Vector loop equation. Scalars next. I'm breaking it down even further than that. We're going deeper, like they did in Inception. So, give me vector loop. Regular vector loop equation. So, coming all the way from the beach, Jackson is giving us an answer. And Rosendo, who will be first. Alright, so Rosendo says R2 minus R41 plus R4. So wait, you did R4 or R1 plus R2 minus R41. No, so this should have been a minus as well. But besides that, you were right. Because these are all going clockwise, these are going counterclockwise. So, R2. Okay, so Jackson, you're right. When you created the vector loop, it doesn't really matter. But for this one, they have given us the vector loop. So let me make this clear. If I give you the vector loop and these arrows are on the question, I expect everyone to have the right direction on it. But when you were creating the vector loop, like for example, when you did it on your exam, I don't really care how you did the positives or negatives. But if I give it to you, I don't want... So let's put it this way. If my solution manual has it as this vector loop right here, it would be very easy. Why don't you guys just follow the solution manual one? Because if you don't, that means I have to go through and make one for everyone's different solution that has a plus or a minus sign. If I give you the vectors, use the directions of the vectors, please. Make it easier for me. But yes, you are right. When you create the loop, it doesn't really matter. But for here, you were given the loop. So please follow it. Plus R1. So this right here is step 1. This is the regular vector loop equation, garden variety vector loop equation. Now step 2, Jackson has already said it, is the scalar equations, and so we are going to write those. Crap, that was really bad. What happens to R1? Assumingly, we know this is a 90-degree angle. What happens to R1 when we take the x component of it? It goes to 0. So we do not need the R1 here because that is this vector going up. All good? Now let's do the y version of this, which is R2 sine theta 2 minus R41 sine theta 41. Anybody else think this is a little tedious? And then the last one, we have a positive component of this, so let's do plus R1. All right. So these are our scalar components right here. Now, the third step was to take the first derivative of these components. So the first derivative of R2 cosine, well, so real quick, actually, before we move on, before we do anything else, we need to know what is changing and what isn't changing, right? Would you guys all agree that we need to know what is changing and what isn't? So let's go through this really quick. Let's start at R2, right? So R2, we know that R2 is changing, but it is the input. So we treat it just like we did our last ones, right? So this right here, we're just going to mark it down as something we know, right? Even though it does change, we will always know what it is, right? And theta 2, similarly, we also know because it is connected to this and it cannot move. This whatever, R2 is directly in line with this, and it cannot move out of this because this is grounded over here. So this straight line is always going to be a straight line. So we'll say that we know both of these, right? We'll just treat it like we did the last one. Now let's go with R41. R41. Move this over here so I can see a little bit better. Junlin says it's known, and he is correct. So R41, let me mark that down. I was trying to get back to what we were doing. Here, let me put theta 41 as well. So R41, good, right? What about theta 41? So let me ask you this. On this exact vector line, will this exact vector line exist however this thing moves? Like, for example, if this pushes the little bar down here, will R41 be on the exact same angle? That is the question. And this one should be so think about it that way. I'm going to draw you the coordinate system too. I'm pretty sure I know how they did it. I think they did it right here, but I'll take a look, actually. Yep, I was correct. So right here, they drew it just a normal coordinate system, but they had it going on the y-axis. So x here and y. I know you can't. It's really hard to see. So essentially what I'm asking is the following. R4, x, y. That right there is theta 4, 1, right? If this thing moves, this paddle moves down to here. Let's say it rotates down as far as it goes. Will this angle still be what appears to be 120 degrees? Which it's probably not exactly that, but it looks like it. So we're using that as kind of a frame of reference for your mind, right? Will theta 4, 1 be that exact same angle? Let's say if it moves down here, where it then looks like this. The answer to this is no. Theta 4, 1 will 100% change here. So, mark that there. So we have one unknown so far. Right? What about R4 and theta 4? Anybody want to take a shot at this one? R4, will that change? So think about this. This piece is rolling across this like slap, whatever this thing is, little pinball slider or whatever you want to call it, paddle. There you go. It's sliding across this. So that means that as this thing rolls across this, or like, this part slides, this part rolls. As it rolls across this, will this vector length stay the exact same? The answer to this is also no. This one will definitely get longer because as this thing moves out this way, this will have to continue to follow it because the vector is created from this part to a part perpendicular straight down from it. And so if this thing moves further out, like way over here, this is going to have to come further out to pick it up, right? So R4 is not known. Theta 4, similarly, will also not be known because theta 4 is this angle right here, right? So if theta 4 is that angle right here, if this thing slides, if this thing rolls across it, this is going to come down. That means theta 4 will now be like this, going out here. Therefore, it will minimize it, or it could go the other way. See what I'm saying? So theta 4 is also not known. Right? We all good there? Does everybody understand that right there? Cool. So, right now, we have 3 equations and 3 unknowns, right? Let me get rid of all this stuff. Or we have 2 equations and 3 unknowns. So we are 1 short. We need 1 more equation to get this right. Would you agree? So what are the rules that I taught you guys on how to evaluate or how to come up with an additional equation? Where on this could we come up with an additional equation that relates 2 vectors together or 2 angles together, something like that? How could we do it? Rolling contact, yes. So that will be something we're going to talk about right after this. But I'm talking when it comes to what this vector loop is showing us right now, how could we come up with another one? Because we will need this one as well. But you are correct. Rolling contact will be one in a second. And I'm going to explain, because the way that the solution does it is kind of confusing, so I'm going to explain it after the fact. Yes, so right here, this will always be a 90-degree angle, right? As this thing rolls down this way, this will adjust and then go straight up to it as well. So that means you could write this angle, or that equation right here as, let me write it right here. I'll do it right here. So theta 4, 1 minus pi over 2. I think this is how they'll write it. Maybe I'm wrong. Is equal to theta 4. We'll see. They might go the other way, but let me look. So they do, yeah, they do it the other way. They do theta 4 plus pi over 2. But once again, it does not matter. Theta 4, 1 minus pi over 2. So right here. So theta 4, 1. And then when you subtract off pi over 2, you get to here, right? So that is our third equation. So now we have 3 equations and 3 unknowns. Perfect. But there is one more that we're going to talk about after or we're going to talk about right now. So right here, there is a rolling contact equation. And what that means is, so let's really quickly, what is the rolling contact for this equation? Do you guys remember what this one is supposed to look like? Give me 1 second. So they write it all out really stupid, and I'm trying to like get it back to where it was. So R4 plus rho 3 theta 3 minus rho 3 theta 4. Minus rho 4. So R4 yeah, give me 1 second. I'm trying to get it back to that's the other side, and this is, because like I said, they wrote this kind of dumb. R4 naught plus rho 3 theta 3 naught minus rho 3 theta 4 naught. Okay. So it's delta R4 is equal to, so we move that back to the other side, is equal to rho 3, yeah. Sorry, it's taking a second. I'm trying to write it out to where it makes sense. Delta theta 3 minus delta theta 4. Okay, perfect. I got it right. So, real quick. So no. So gentlemen, you are correct. You are close though. Like what you have is correct. It's so the general equation that you have is right. So for this one right here, it is, remember, it relates. So remember what the rolling contact does. For this one in particular, it relates the angle change of this right here, right? Right? The arc length of this one to the amount of distance you've traveled on the surface. And so, remember, what is the distance we were traveling on this surface? It is R4, right? Would you agree with that? R4 is the amount of X distance we are traveling here on this paddle. So R4 is the one you have to have there. Or, so yeah, it's the change in R4. But remember, there is a, this one here, let me see if I'll actually go find this one in particular in the previous chapter. Because that is something that we'll need to look at. I'll go find it. Yeah, there it is. So right here is the one that we're looking at. We're looking at this right here, because remember, the angle is changing on the bottom, and it's also changing, on here on this. So essentially, how this one is written is, we have the change in R, so delta S, so delta R4, for how our question is, delta R4 is equal to row 3, because this on our problem is link 3, so this is 3 on our problem, so it would be row 3 times delta theta 3, because remember on this question they're showing this as 2, so delta theta 3 minus delta theta, so this delta theta right here is the angle change of the flapper here, or this like surface it's on. So for our question that is 4, so it's delta theta 4. And I'll go back to it in a second so you can look at why it's like that. But this is what ours should be. So let's go back really quick. So right here, these are the things that are, for the rolling contact, these are the things that we are worrying about. This right here is link 3. So remember, we are trying to relate the arc length of this roller to how far we are moving on this slider. And so the two things that are working in conjunction with this is link 3's radius and link 3's angle change, which link 3 is the circle, versus this vector length change, right? So, because remember, as link 3 is rolling, R4 is getting longer, right? So, if you write this out, it is delta R4. So essentially the change in R4 is equally related to the radius of 3, this is the arc length equation, by the way. So it's the arc length, it's the change in angle 3, which is this angle right here. Essentially it's like this, as this thing's rolling across, right? Minus delta theta 4. Because remember, this one is different than the normal rolling equation, because this thing is also changing angle. This paddle is also coming down. If this were just a flat surface, this part wouldn't exist. It would just be theta 3 minus theta 3 naught, right? But it isn't, because that part exists because this thing is all spinning. So we have to relate it one angle spin to the other one spinning as well. So this is our equation, right? And so someone else in here is probably going to say, they're going to go, well, wait a minute, didn't we just add an unknown, right? Theta 3 is something that we have just added, correct? Is that fair to say that theta 3 is now something that we do not know? Anybody want to take a stab at that one? Because remember, R3 was not a vector. We did not have an R3 or a theta 3 in our vector loop. So therefore, this is a completely new variable, right? So Jackson, this is exactly why I said that we needed this extra one right here, because we added one right here. So essentially we ended up with 4 equations and 4 unknowns. This is the reason why. And the book doesn't explain it. They kind of do it all at the same time. They don't do it at the end. They just kind of say, this is the rolling contact, this is this additional equation. But you probably would have wondered why. Why did we need this one? This is the reason. The reason is because we added an unknown, because theta 3 is an unknown. It is this angle change somewhere on here, right? And so we needed to know, basically, if we would have not had this equation right here, we could not have solved for this over here, because theta 4 can be solved through this right here. And if this theta 4 is not known, you cannot solve for theta 3. You see what I'm saying? Yeah. So just be careful. Make sure. So here's what I would say. Make sure. So without using rolling contact, if you find out that you have 3 unknowns and 2 equations, find something like this. Find something like this. And then when you make the rolling contact equation, it might end up to where it adds an unknown, but it also fixes itself because you added an equation and you also add an unknown. And if you add an equation and you also add an unknown, it pretty much cancels each other out. So that is why unless the things in the equation aren't relatable, right? If they don't actually relate to anything, then it doesn't help you very much. And another thing, whenever you do the rolling contact, make sure that you stick to naming it like this. So you name it by the link name. Do not name it by, try not to name it by vector. So for example, this question was very smart. As you guys can tell, they did not name anything with link 3. They did not go, oh, well, R2, R3, R4, and R1, because that would have been confusing, right? Because then you would have had the theta 3 here, and then the theta 3 would have also been here. You see what I'm saying? So essentially, if you have a rolling contact, name things differently than the rolling contact to not confuse yourself. So for this question, don't name anything in the vector loop that is 3. Don't go R3 or R31. Name this one. Basically save the rolling contact for its own vector or its own name, because if you do that, you'll end up with multiple theta 3s and it'll confuse the crap out of you. So don't do that. And remember, you can name things whatever you want. It doesn't matter. Just make sure that you keep it consistent and that you don't change things halfway through. So, that was our rolling contact equation. I will rewrite it over here. So, delta R4 is equal to rho 3 delta theta 3 minus delta theta 4. All right, cool. So the last thing we're gonna do really fast is, so I know you guys probably can figure this out. You know, we've done this now where we've taken derivatives and all that. I'm sure people are, you know, well on that one. But we're gonna do one derivative really quick of one of these, and I'm gonna show you how much of a pain it can end up being, right? So I need to get rid of this though. So real quick, where am I looking for it? All right, this is what I was looking for. So real quick, we're going to just do the derivative of the x equation. That's it. So if we do that, we end up with R2, well, minus R2, sine theta 2, plus R4 1, because remember R4 1 is not changing, so that is essentially a constant here. H4 1 sine theta 4 1. Now here's the part that I was going to stress on you. This part right here. If you guys recall, R4 and cosine theta 4 are both unknowns here. So you have to do the product, or the product rule with this one. So minus R4, well, if you take the derivative of R4, remember, you get an F4, right? Cosine theta 4. And then if you, this one would be plus, it stays plus, okay. And then you would do R4 sine, wait a minute, no, that should have been negative in the middle, I think. Wait a minute, yeah, it should have been negative. Sine theta 4, right? So essentially, oh, and there should have been an H there. Aha, I caught myself. H, thank you, gentlemen, you are correct. So a R4 H4. So now, if we move on to the next step, this is where I tell you that things get a little weird, is because now, if we do the next step, you do the derivative of this one again. So let's do the derivative of this one again. We do minus R2 cosine theta 2, cosine theta 2, cosine theta 2, right? And then you do plus, take the derivative. Remember, R41 is constant, so we're good here, so leave that on the outside. You do R41 times H41 prime sine theta 41 plus H41 prime, or H41 squared cosine theta 41. So that's not anything new. This last part is the thing that's new to us. So let's bring this down here. So minus, which is this part right here. Now we have to take the derivative of this and this. So let's start with the first one. So take the derivative. Once again, though, these are both variables. So therefore, we have to do the product rule again. So we have F4 prime, right? And times cosine theta 4. And then plus, and this one flips around, right? Yeah, so this one now becomes a minus, yeah. Minus F4 H4, right? Sine theta 4. That's the first part, right? And then subtract, although you have to you move these signs through. So this one's this one is negative, that one's positive, so I have to change that really quick. So then plus, now the next part. So then R4, H4, and theta 4 are all unknowns, right? So then we have to do this is the time I told you we have to do the triple product rule. So you have to do R4 or R4 goes to F4, and then you leave all the other ones the same. So H4 sine theta 4, and then you do plus. The next one would be R4 the same, H4 prime sine theta 4, and then also you would do the last one, which would be R4 H4 right? So R4 H4 squared cosine theta 4. So do you see how this very small equation can get rather large very fast? This is what happens whenever you have multiple variables in the same section, like cosine, or if like it's theta 4 and R4, they can expand like this. So for the triple product rule, it's pretty straightforward. You do the exact same thing, except that you just do this one first, leave these two the same. Then you do this one, leave these two the same. Then you do this one, leave these two the same. And so this is what it turns into. So like I said, these equations can get quite long, but as long as you stick to the derivatives, you will be fine. I'm actually going to see if I got this right, because I really want to make sure before we move on here. So let me see. So this is differentiation, that's the first one. Secondary, so this is the first equation. So minus R2 cosine theta 2 plus R4 H1 prime sine theta 4 plus R, yep, okay, I got that one. Minus F4 cosine theta 4 plus 2. What did I do there? Did I miss? Oh, you can add these two together. Yeah, I always forget that. So these two end up being the exact same thing. So if you make this a negative, make this a positive, this F4 H4 sine theta 4 is the same here. So it's 2 F4 H4. I just didn't simplify, but sure. R4 H4 prime sine theta 4, which is here, and then R4 H4 squared, so we got it right. Now one more thing before I let you go. When you do these derivatives, you also have to take derivatives of the equations that you created, not just the scalar ones. And the reason is because, once again, if we're trying to find a velocity or an acceleration, and this right here is still in this form, it does not give us a velocity or acceleration. But the good news is that this is really easy to take a derivative of, right? So let's start with this one right here. That's the good news. So if you take the derivative of theta 4,1, theta 4,1 is just what? h41. Take a derivative of pi over 2. It is a known constant, which means that it goes to 0. So theta 4,1 is equal to h4. Or h4 is equal to h41, or h41 minus h4 is equal to 0. So that's the first one. So essentially you take a derivative the exact same way. Oh, I think I got rid of something there. Oh, okay, yeah, it was just that. So it's the exact same, and I think that's what they end up getting here. Yeah, so you can see that they got it right here. That's the first one. And then you would take the derivative again, which would be h4 prime minus h41 prime. You see, you just do the exact same things. You take a derivative of an angle, you get an h. Take a derivative of a length, you get a f. So it does not change. That part's really easy. Now we're going to do this one right here. So if you expand this right here, so you have to expand this equation. So we have to do the rolling contact. So delta r is equal to r4 minus r4 naught. Remember, r4 naught is the original position of r. Is equal to rho 3 times delta theta 3. So once again, delta theta 3 is theta 3 minus theta 3 naught, right? Minus theta 4 minus theta 4 naught, right? So real quick, what is R4? Is that a known constant to us? Or R4 naught, that's what I meant, R4 naught. R4 naught is just the starting position, right? And we know what the starting position is. So, basically, all of the knots go away. And you're left with F4 is equal to, I think rho 3 stays, and you get H3 minus H4, which I think is what they end up getting here. Yep, they do. Because you can see it right here. Although they take the derivative of it again. So it is right. Let me get rid of all this crap off the screen. It'll be more easy for you to tell what's going on. So, does everybody see how that works? Is that essentially you just take the same derivatives that you have been, except you have to do it with your rolling contact and your additional like angle equations or something, right? And then, as you can see, they got it right here. They just like to move things all to one side, but if you move this back to the other side, you would get the same thing, right? And then it'd be F4 prime is equal to rho 3 H3 prime minus H4 prime. You guys see? So basically, when you get additional equations, you have to take the derivatives of those as well. Along with the scalar equations, you have to take double derivatives of those as well. So we went over today. Well, I don't even know if we went over, honestly, because this class, I'm pretty sure summer class, they're supposed to be like an hour and like 10 minutes or something, but we generally don't go that long. So I'm going to take attendance really quick. I'm going to go ahead and shut off the stream. And once I have taken attendance, you guys are free to go. So let me do that real fast.